use pump to pump the water. Okay, so you have two devices which is commonly used to force the liquid. Okay, if the liquid is gas, we normally use fan. If the liquid is water, we normally use pump. Okay, to make sure that they flow. Okay, through a channel, which is pipe, most of them. We pay particular attention to friction. Yeah, this is where it goes to friction, because it's actually the friction. Friction is the culprit. Yeah, friction is the cause why you have head loss. Okay, friction is the main reason. If you study thermodynamics, this is one of the reasons which cause irreversibilities. Okay, this is one of the reasons which cause irreversibilities in an application. All right, if you study thermodynamics, I think this is the later part of thermodynamics, which is but then again, friction is one of the main reasons you have a loss in performance. Okay, just put it down that way: loss of performance, or loss of efficiency due to friction. Okay, friction is then causing the pressure drop and head loss. Okay, in pipes, pressure drop meaning, okay, you have lower water pressure. I think you experience that. I think most of us. I mean, if you ever stayed in residential area, in coaching area, in some of the city areas, then you'll know. Okay, you'll know there are times when you have low water pressure. Okay, you curse someone, and you curse, you menyumpah siapa-siapa lah. Okay, the water agency, now. Okay, it's actually because of low water pressure. It's actually due to friction. Okay, it's actually due to friction. How would you reduce the friction? All right, how would you reduce the friction? Okay, that's the big question. And head loss. Okay, just now we talk about okay, if you're staying in flat, okay, in the seventh floor, okay, flat on the seventh floor, but the water is only capable to be pumped up to the fourth floor. So the losses of height, okay, from the seventh floor to the fourth floor is what we call by head loss. Okay, is inability to pump the water higher. Okay, that's what we call by head loss. The pressure drop, I think you recognize this pressure drop. Okay, by having like lower pressure, okay, of water. Okay, when you want to use the water, right? Okay, well, the pressure drop is then used to determine the pump. Okay, the pressure drop will be used to determine the pump. Right. Just now I told you about like the use of pump. Okay, when you go to the hardware store, okay, they have like different power. Okay, a pump of different power. They'll tell you this one is 0.5 horsepower. It's probably 1 kilowatt. This one is 0.5 kilowatt. This one is 2 kilowatt. So which one would you choose? Okay, it depends on the application. Okay, it depends on the pressure drop. Right? It depends on the pressure drop. If the pressure drop is more, then you'd have to use a higher pumping power requirement. If the pressure drop is insignificant, then you just use a little bit less. Okay, pumping power requirement. Okay, so on and so forth. So you have two type of piping channels. Okay, you have two types of piping networks. Okay, this one is a circular pipe. This one is rectangular duct. Okay, we call this a rectangular duct. We call this a circular pipe. Normally in application, right? Normally in application, if you ever work in buildings, then you'll see that most of the water, okay, most of the water channels, okay, most of the water, when you have water flow application, it is normally contained in a circular pipe. Okay, remember, fellas, when you have water application, it's normally in circular pipe. I think you've never seen like rectangular pipe. Have you seen one? If you ever seen one, then you let me know, because there is a certain disadvantages. There are certain disadvantages. Okay, if you use rectangular duct, okay, for water flow, for fluid flow. Okay, because okay, the circular pipes can withstand larger pressure differences between the inside and the outside. All right. Compared to rectangular duct. Okay, that's why rectangular duct is normally used in application of air, in gas application. Okay, in gas application, just like okay, but even so, you still have like gas using the circular pipe as well. Okay, circular pipe, rectangular duct, rectangular duct. Either way, I mean the water will normally use like circular pipe. Rectangular dark is normally used when you have um, gas application or air application. Okay. Now this, okay, the theoretical solutions are obtained now. How would you differentiate the correlations related to the water flow? Now this is water flow, right? Okay, this is the water flow inside a pipe. Okay, can you visualize this? Why this is what we call by a velocity profile, yeah? Okay, this is what we call by velocity profile. This is the V average. Okay, this is the V average. How so? Do you understand this, fellas? Before we move on, all right, before we move on to the other part of the lecture, do you understand this? Why is it going like a bullet, like they have the bullet kind of pattern here? Why is it so, fellas? Do you understand this? Okay, do you understand why the velocity profile is in such a way? This is due to friction, yeah? Okay, when you have pipe, okay, this is the pipe, right? This is the pipe. You have friction on the wall, of course. Okay, you have friction on the wall. You will have friction on both walls. In fact, on all the walls of the circular pipe, right? On all the walls. Now, remember, when you have wall, then you will have friction. Okay, when you have fluid flow and the wall and a solid surface, you will have friction, fellas, right? And the friction will lower down the velocity. The friction will lower down the velocity. So that is why the closer, right, the closer the liquid is to the surface, the lower the velocity is. Do you understand that, fellas? Right? You have water flow inside a pipe, right? Okay, you have water flow inside a pipe. Due to the friction on the wall, it reduces the velocity. So that's why the farther away it is from the surface, okay, from the side surface, the higher the velocity is. So that's why this is okay. Let's say this one's the reference point, datum we call it here, reference point. The one in the middle will exhibit the highest velocity. Okay, this is what we call by Vmax, right? And the one that is closest, okay, the one that's closest, okay, to the surface, we call the lowest velocity Vmin, right? And I think if you, I'm not so sure though, if Miss Ayn touched on this, but the moment the velocity on the surface with friction, we call that as no slip condition. Have you heard of this, fellas? Pernah dengar tak no slip condition?
Pernah, sir.
Ah, cool. Right. We call it no slip condition due to the friction. Okay, due to the friction. So that's why the velocity on the surface here is what we call by velocity when it touches the surface, we call that as zero. Okay, we have zero on the surface, we have maximum, okay, in the middle, okay, in the middle, the farthest away the liquid is from the surface. So that's why you have zero and then it goes all the way up until the maximum. Then the maximum when it's approaching the surface, it goes back down until it reaches zero, no slip condition. So this is the velocity profile of water flowing inside the pipe. Okay, flowing inside the pipe. So the velocity average here is representing, okay, on a cross section, right? Is taking zero plus this plus everything plus the maximum plus the minimum. You divide, then you have the V average is somewhere here. If you do the calculation, we're going to be using the V average most of the time, fellas. We're not going to take here. We're not going to take here because we're not going to take here because it will be incorrect, right? Okay, it will be inaccurate. Okay, if you were to take the readings from here, if you were to take the readings from here, if you were to take the readings from here, it's not going to be accurate. That's why in any particular assessment, okay, of the fluid mechanics and of fluid flow, we're going to be taking the average, right? Average velocity of the water inside a pipe. Okay, we must rely on results. Okay, fluid flow problems. Okay, um, to form the analytical solutions. We have numerical solutions, we have analytical solutions. Okay, analytical solution, it comes from experiments. Okay, it comes from experiment. Here it tells you how to get the M. Okay, the correlation between M and then I think I'm not really explain this to you. You're gonna have headaches, right? I just want you to remember this. M equals to rho AV, that's it. Okay, the simplest form of how we can measure the mass flow rate of any fluid, okay, inside an enclosure, particularly pipes. We're gonna have a circular pipe. This is the mass flow rate. Okay, the mass flow rate equals to rho v average, and then the area of the circular duct, right? Or you can write it down in this form as the v average can be calculated by using this equation, right? Okay. So we're not really going to go into the equations now. We would rather use the equation for an equation at all. Okay, you don't have to worry about that. Now the second part of the lecture is on laminar and turbulent flows. Okay, now we are going to study, like I told you. Okay, we have different type of regimes. I call it a regime. I call it a regime or different type of flows. Okay, different type of flows. Right, you have actually, okay, just for a normal flow, okay, for a normal water, you have water flow, you have laminar and turbulent. Okay, that is normal. You have laminar, you have turbulent, and then you have something in between, right? Okay, for any water flow, for any fluid flow, to be honest, okay, any fluid flow, in fact, whether it's gas, whether it's fluid, you're gonna have three different regimes. Okay, you can have three different regimes, right? You're gonna have three different regimes. The first one being laminar. You're going to have laminar flow, and then you're going to have turbulent flow. And then you can have a mix between laminar and turbulent. We call it transition. I think this one has different names. Yeah, it has different names, being transition flow, being a wavy laminar, being a mix between laminar and turbulent. They have different names for this. Okay, they have different names for this. But I do want you to remember that the flow will consist of laminar and turbulent, and this one is a mixture between laminar and turbulent. All right. In this book, it is called transition. In some of the books, they will call that as wavy laminar. Okay, they will call that as wavy laminar. Okay, right. Okay. Laminar and turbulent flow regimes of candle smoke. Right. Okay. So you have laminar flow, you have turbulent flow. Okay, of candle smoke, and then okay, this is the experiment. This is the experiment that we can use in order to evaluate the regime. Okay, the regime of of the flow, or the regime of the flow. Right. We have this. In fact, four, in lab four, which I think you shall do in year three or year two. I think it's year three now. They just changed that, right? You have a device. We call that as Reynolds number experiments. Okay, we call that as Reynolds number experiment. We have this setup. Yeah, you can view. We have a die. Okay, we have a die which we put. Okay, we're gonna put in the middle. Okay, like I told you, if you study about the velocity profile, okay, if you study about the velocity profile, we're not going to put this die very close to the surface because it will exhibit the what do you call that, the feature of friction. So that's why when you want to put this die, make sure it's in the middle. Okay, if you want this experiment to be successful, you might want to put this one in the middle. All right, this die. Okay, for laminar type of flow, for laminar flow regime, you're gonna have a straight line like this. Okay, we're gonna have a straight line. So that's why in laminar flow, it is called a streamline flow. Okay, laminar flow is sometimes referred as streamline flow because you have like a straight line. If you were to do the experiment, this dye experiment, right? You're gonna have a straight line. You're gonna have a straight line. This is what we call as laminar flow. Okay, you can have straight line, and then just okay, highly ordered motion. Okay, that's another definition of laminar flow. Highly ordered, meaning is in order. Okay, it's in order. Smooth. Okay, smooth streamlines. Okay, in this instance, most of the time the velocity is very low. Okay, in this instance, most of the time in laminar flow, when you have very low velocity, you're gonna have a straight line like this. Okay, you're gonna have laminar flow. And the moment you increase the velocity, this is the findings from the experiment. Yeah, the moment you increase the velocity, you're gonna have the flow. Okay, the flow being distorted like this. Like you're gonna have distortion in the flow, right? You're gonna have the flow. Sorry, you're gonna have a disordered motion. This is disordered. Okay, it's no longer straight. Okay, you're gonna have disorientation of the dye. So this is what we call as a turbulent flow. Okay, turbulent flow. So how does this transition flow look like? Okay, it's gonna be like a mixture between both. Sometimes it's going to be straight, sometimes it's going to be wavy, sometimes it's going to be disoriented. That is what we call as a transition flow. Okay, it goes straight, it goes disoriented, it goes straight again, disoriented. It's a mixture between the laminar flow and the turbulent flow, and that is what we call as transition flow or wavy laminar flow. Okay, so these are the regimes, okay, the type of flow that you will encounter in pipe. Why do we need to do this? Why do we need to understand this, fellas? Okay, why do we need to understand this? Because different type of flow, different type of laminar, turbulent, or transition is going to give you different forces acting on this. You're gonna have different forces, fellas. You're gonna have different energy in order to work with this. You're gonna have different type of pump that you shall work with, right? For a low level, for a low level like velocity, okay, when you have this, well, most of the time the velocity is very low. Okay, you're gonna have low pressure, you're gonna have low everything, so everything is smooth. So in this type of application, you're gonna be using a low pump requirement for this kind of flow, for laminar flow. For this one, you would have to use a higher pump requirement for this one. Okay, so that's why it depends. And furthermore, not only this, it depends on the type of flow, it depends on the surface area, it depends on the material of the pipe, and so on and so forth. There are so many things to remember. But most, I think most of all, I think you'd have to consider the type of regimes that they use, okay, to evaluate this, right? Because the type of regime here is going to play a major role in determining what will be the requirements required for a type of flow, okay, the flow inside our pipes, right? So that's on laminar and turbulent flow. Now we move on to Reynolds number. I think in previous chapter we learned about Reynolds number. Okay, somebody asked me, what's Reynolds number for? Okay, what is Reynolds number for? Reynolds number is to determine whether it's laminar, whether it's turbulent or transition. Okay, that is the usage of Reynolds number, right? If you ask me what is the use of this Reynolds number, is actually to determine whether the flow is laminar, whether the flow is turbulent, or the flow is transition. And that is it. Okay, I repeat, Reynolds number is used to determine whether the flow is laminar, whether the flow is turbulent, or whether the flow is transition. And that is it. Nothing more, nothing less. Okay, nothing more, nothing less. So that's what it is, right? If you need to know whether the flow is laminar, if you need to know whether the flow is turbulent, or you need to know the flow is transition, you can get that information from Reynolds number. And how would you determine the Reynolds number is by using this equation? Simple, right? You can read all this stuff, or you can read all these blah, 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 blah. It's actually just this Reynolds number equals to this. Now mark my word. This is the only thing that you need, okay? From this slide, this is the only thing that you need. A Reynolds number equals to this. That's it. Rho VD over mu. Or we can write it down over nu here because rho over mu is equals to this. Okay, it's simple, right? It is simple. Now the definition, all right, okay, you can read this. Okay, Reynolds number is inertial forces, viscous forces. What? Okay, the transition from laminar to turbulent depends. Okay, then you can read the rest. Okay, you can read the rest. Right, okay. The transition from laminar to turbulent flow depends on geometry, like I told you. Okay, there's so many factors. There's so many factors that influence the type of flow in a pipe, right? It could be the geometry, like I told you, we have different geometries for the pipe, right? We have different geometries for the pipe. You have a circular pipe, you have rectangular pipe, you have triangular pipe, and so on and so forth. All right, we'll see that. Okay, I mean you have different type of pipes, in fact, right? But it's not going to be economical or logical if you use some of the geometries, to be honest. Right, surface roughness, exactly. All right, surface roughness is of course okay for different material. It's going to give you a different surface roughness. And then you have the velocity, and then you have the temperature. Yes, if you work with I mean, if you stay in a place with winter, then I think sometimes we have to use like a heated type of water. Okay, you have to heat up the water so that the water won't be frozen. Okay, you have to heat up the water. Okay, in pipe so that the water will not be frozen inside a pipe. Okay, soil water temperature, and then the type of fluid, all right, the type of fluid that we're dealing with. And you have to remember that inside a pipe, it's not always water. It's not always water. You know, sometimes you put refrigerant inside a pipe. Okay, we have refrigerant. Okay, we have a different type of fluid which could be flowing inside pipe. So different type of fluid will exert different regime, whether it's laminar, whether it's so it's different. Okay, it's different. So have a look at this geometries with roughness, velocity, temperature, type of fluid. This factors will influence whether the flow is laminar or whether the flow is turbulent inside a pipe. Okay, inside a pipe. So how do you determine? Then you just use this in order to determine whether the Renault number is whether it's turbulent or whether it's laminar. Just use this. Okay, use this. Renault number is this. Okay. Critical Renault number. What is a critical Renault number? Okay, critical Renault number is the moment when the fluid turns turbulent. That's it. Right. What is critical Renault number? Critical Renault number is the moment or the value at which the flow turns turbulent. Okay, that is the critical Renault number. And this value differs. Okay, this value differs um, in different circumstances, in different geometry, in different roughness, velocities, fish temperature, type fluid. Okay, it differs from one fluid to another. So that's why the study of fluid mechanics is diverse. Okay, is quite complicated, right? You need to understand a bit more. Okay, you need to understand a bit more. So that's why Renault number. Seeing this, okay, Renault number is going to determine the type of flow inside a pipe, meaning Renault number is one of the most important correlation or equation, okay, that we shall use in a study of fluid mechanics. Okay, it's very important, fellas. Right, at large Renault number, the initial forces which proportional to the fluid density at the square, okay, thus the viscous cannot prevent the random rapid fluctuation. Okay, well, I can read this, right? But most importantly, this, the Renault number is given by this, right? And the critical Renault number changes, is a point where it changes to turbulent, okay? And this value, it differs for different geometry, roughness, velocity, temperature, as well as type of fluid. Okay, so that's it about Renault number. Right, okay, D here. Okay, you have the rho Vd over mu. D here is actually hydraulic diameter. Okay, dH here is hydraulic diameter. It's not just D, yeah? It's not just D. Okay, rho Vd over mu. Okay, rho Vd over mu. Sorry, rho Vd over mu. This D here is actually hydraulic diameter. Okay, hydraulic diameter. So for flow through non-circular pipes, okay, you have different geometries, like I told you. You have different geometries. You have circular tube, you have square duct, you have rectangular duct, you have channel. So for um each of these, okay, for each of these, for circular tube, the DH here is D. Okay, because the DH is actually full area of the circular pipe. Okay, full area divided by its perimeter. Okay, this is it. I mean, 4 AC, 4 area, 4 times area of the circular duct divided by its perimeter. Now, if you were to calculate this, okay, so you expand this. This is pi d square over 4, and then the perimeter is pi d, and then you divide this. Okay, everything you're gonna have d. So that's why you put d inside this equation. This is not just literally d. Yeah? This is not just the diameter. It's actually the hydraulic diameter. Okay, hydraulic diameter is given by this equation is 4 area of the circular duct divided by the perimeter. Same goes for this one. Okay, for a square duct, this is what is going to be. For a rectangular duct, okay, this is what is going to be. And then for a channel, this is half field channel. Okay, this is what is going to be. So the hydraulic diameter is the one that's being used in this equation, not the diameter itself. Okay, it's the hydraulic diameter. Okay, rho Vd, d here is the hydraulic diameter. Okay, right. Okay, for flow inside a circular pipe. Okay, for a flow inside this. Okay, if we were dealing with pipes at our home, We're dealing with pipes elsewhere. Okay, dealing with water in pipes. Actually, the value is here. If the Renault number is less than 2300 is laminar flow, fellas. Right? We just studied about different types of flow. Okay, if the Renault number is less than 2300, you're gonna have laminar flow. If the flow number is greater than 4000, this is the critical number. Yeah? Okay, this is the critical Renault number. If it's like uh, the Renault number is 4000 or greater than 4000, beyond 4000, we call that flow as turbulent, right? We call that flow as turbulent. Now have a look at this. Okay, you have laminar, you have turbulent, you have laminar. This is what we call a transition flow. Okay, this is a mixture, right? You have straight, you have disoriented, straight, disoriented. Again, this is what we call by wavy laminar, right? So you have flow inside a pipe. If the Reynolds number is less than 2300, it's laminar. Okay, how do you calculate the Reynolds number? Is from this equation, rho Vd over mu, right? Reynolds number equals to rho Vd over mu. Now, the moment Reynolds number exceeds 4000, this is the critical Reynolds number. The moment the Reynolds number is greater than 4000, it becomes turbulent. Okay, just what being said here. Now, in between the two to 2300 and 1400, okay, it's transition, right? In between these two values, okay, if it's like less than 2300 is laminar, if it's greater than 4000 is turbulent flow. What if it's in between these two values? Is transition. Okay, it's just that simple. I think in your task, okay, in one of the labs, I think one of the modules in lab 4 is to find this critical Renault number. Okay, that is your task. Okay, in lab 4, you would need to find the critical Renault number. This is the experiment you have to do. Right? Okay. Uh, right. You guys want to take 5?
Sure, sir.
Yes, yes.
Okay, so we take 5. I know it's a bit heavy to take because I think the next one is the one that's important. Okay, I want to take 5. I'm not going to go straight with lectures. We only like nine slides and now it's only 8 slides. I should talk less, right? Should talk less. Just a few more slides for us before we conclude this lecture. Just a few more slides, right? We'll take 5. Right, we'll take 5, and then we continue again with 8.4, which is the important part of the lecture. How would you determine the pressure loss, the head loss? Okay, that's basically what we shall look into. Right, is session 8.4 that determines the whole thing. Right, don't worry about this. I'm not gonna make your life miserable. We can talk about this, but you're gonna get crazy. Okay, but what I want you to remember is this. Okay, this is the most important ones, the one in blue. Okay, forget about this. This is how they got the whole equation. I want you to remember this. This is most important. Okay. We'll take 5 starting now. Okay, selamat datang kembali. Right, so I think we shall continue. Okay, this is the last part that we shall cover together in this lecture. Okay, after this, we're going to try doing some exercises, all right? We're going to try doing some exercises, okay? So laminar flow in pipes. Okay, we consider steady laminar incompressible flow fluid. Let's consider some properties in a fully developed region. Okay, blah, blah, blah. It's actually talking about this. And okay, you have the two profiles. Okay, you have the P profile, and then you have the okay the stress. Okay, shear stress profile. Okay, plus dr in the radius direction, dx. Okay, in the x direction. All right, they do this. Okay, we're not going to talk about this. In a fully developed. Okay, there's a fully developed laminar flow. Okay, this is velocity profile. Okay, each fluid particle moves at a constant actual velocity. Okay, along a streamline velocity. Okay, you are remain unchanged in the flow direction. There's no motion. Okay, to develop this blah 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 diagram, the thickness. Actually, they end up with this. Okay, this is what I want. Right. Okay, it's actually, they are actually developing the pressure. Okay, the pressure drop, the pressure change from point one to point two. Okay, point one to point two, and this is um okay the equation. Okay, this is equation, and the pressure drop between point one to point two is what we call as pressure loss. Okay, the PL. A pressure drop due to viscous effect represents the irreversible pressure loss, okay, and it's called the pressure loss, right? Okay, pressure loss is the difference between the initial pressure and the final pressure, and the difference is what we call a pressure loss. Okay, the bigger the difference, the bigger pressure loss. 'Cause we don't want the loss to be bigger. Actually, we just want we want to minimize the what they call that the the losses. Okay, we want to minimize the losses, and in order to minimize the losses, there are many ways. Okay, there are many methods that we can employ to reduce the losses. Okay, pressure drop due to viscous effect represents the irreversible atocho. If we study about thermodynamics, this is one of the irreversibilities, okay, that we have to encounter. This the friction. Okay, friction. Okay, viscous effect is coming from the friction, and then is one of the cause which is causing the pressure loss. Okay, from the pressure loss, right? Pressure loss. I'm not asking to develop this. Okay, you don't have to worry. This will not come out in a test. Okay, what I do want you to remember just this: the pressure loss. Okay, given by this. Okay, is given by F being the Darcy friction. Okay, it is it's from this. Okay, they just right, they just make it simple for you people to see. Okay, the pressure loss is FL. Okay, um, L here being the length. Okay, the length of the pipe, and D the diameter of the pipe. Rho V square over two. Okay, rho being the density velocity over two. Okay, I repeat, the pressure loss delta PL equals to F. That's the friction factor. Okay, this one represents the friction inside the pipe. Okay, that's the friction factor. It represents the friction inside the pipe. And then you have L, which is the length of the pipe. D is the diameter of the pipe. And then you have rho V square over 2. Okay. F, circular pipe laminar F equals to, okay, for laminar is 64 over a Reynolds number. For laminar, okay, because we are studying about laminar flow in pipe, okay, which is the slower type of flow, which is the streamline flow, okay, highly organized flow, right? So this is the F for Reynolds number. Okay, let me tell you something, right? For F, it will vary depending on the type of regime the flow is. Okay, the pressure loss is FLD. Okay, this equation is fixed, can be used for both, for all the regimes. This one also can be used for all the regimes. However, this F here, it depends on the type of regime. If it's laminar, then 64 over a Reynolds number. But if it is like um turbulent, it's gonna be something else, or it's gonna be something else. We would do something. So that's why we're gonna be looking at exercises. How would you do this? Right? How would you do this if it's like laminar, if it's like turbulent, okay? But first we shall do laminar. In laminar flow, the friction factor is a function of Reynolds number. It's only independent of the roughness. Okay, it's independent of the roughness. It just depends on the mu. It just depends on rho dv. Okay, velocity, the diameter, the rho, as well as the viscosity. This is dynamic viscosity, right? The head loss represents the additional height that the fluid needs to be raised, okay, by a pump in order to overcome the frictional losses, okay, in pipe. Okay, this is the additional height, okay, that a pump must cover, okay, due to the losses from the friction. Okay, so this is the head loss, this is the pressure loss, right? And these are the equations that you must use in order to work out how much will be the losses, how much it will be the head loss. Okay, why do you need to find this? Because the moment you have this, you multiply with the flow rate, the volume flow rate, you can find the pump power. Okay, that's it, right? Okay, the relation for pressure loss and head loss, the pressure loss and head loss is one of the most general relations in fluid mechanics, and is valid for laminar and turbulent flow, like I told you. Okay, this equation, the pressure loss as well as the head loss, they are both they are they're applicable for both laminar as well as turbulent flows. Okay, circular or non-circular pipes and pipe with smooth or rough surfaces. So it depends. You can use these equations regardless whether it's circular or non-circular, whether it's smooth or rough surfaces. Okay, whether it's a laminar or turbulent flows, right? You can use this, the pressure loss as well as the head loss equation, right? So that's the good thing about this stuff. Okay, you can use these two equations, okay, to work out the pressure loss as well as the head loss, right? Okay, so this is right. This is the pump. Okay, the pump requirement. Okay, this is the pump requirement. Like I told you initially, I mean, if you have like the shortages of the height, okay, shortages. Okay, this is the head loss, right? It represents the height. Okay, the height loss. Okay, it represents the height loss that should be able to be covered by the pump. However, due to the friction, is lower than the expected height. So in order to cover the head loss, we must have a pump. Okay, and the pump is the volume flow rate. Okay, the volume flow rate here multiplied with the delta PL. This is the pressure loss. Okay, this is the pressure loss. Okay, so you have V multiplied with this, and initially that we know this is rho GHL. We know this, the pressure drop. Okay, the pressure drop is rho GHL. Now, the moment you have rho multiplied with V here, the flow rate, the volume flow rate multiplied with rho, you have mass flow rate, right? Mass flow rate GHL. So W pump can be calculated by using this equation, right? W pump, the pump requirement, okay, equals to mghl, mass flow rate, the gravity, and HL, the head loss. Okay, right. Okay, so you have horizontal pipe. Okay, this is the average velocity for horizontal pipe. We can use this correlation to determine, okay, the average velocity, and then you can determine for horizontal pipe. Yeah, you can determine this horizontal pipe, the volume flow rate of horizontal pipe by using this equation VA, right? VA, because that's, and you put down this equation, and then you get this in the end. So this is um Poiseuille, Poiseuille law. Maybe that's how to pronounce the name, right? This is another law that's been given by this fella. It's actually how to work out the V, the mass flow rate. Okay, mass flow rate as a function of this. Okay, mass flow rate is a function of this. Now, why do you need this? It's actually showing, right, the delta P here. Okay, delta P. Okay, before that, okay, let's look at this. I think I told you, right? I told you the pump power, right? I thought this is one of the real life application. Okay, real life application. If you have lot of losses, right? If you have head loss can come from friction. Okay, in fact, you know what? Again, and in our lab 4, we will be able to see like lots and lots of losses. Okay, losses. So you'll be studying about losses. Okay, losses due to bends, losses due to the surface, losses due to the pipes, and so on and so forth. Um, constriction and so on. Okay, in one of the labs in lab 4, in one of the modules in lab 4, the head loss here. Okay, head loss here due to the friction. Um, How would you reduce the head loss? Okay, that's the big question that I'm going to ask you, fellas. Because if you have bigger head loss, you're going to use more pump power, right? Higher head loss, if you have greater losses, okay, regardless whether pressure loss or head loss, you're going to have higher pump requirement. You're going to use more power in order to pump the um, in order to pump the liquid. One of the ways that you can do, okay, is one of the ways is to increase the diameter. See, now have a look at this example. Yeah, okay, you have one example, right? You have one example. Okay, D smaller. Okay, D smaller, and then by just increasing the D, have a look at the pump power for this one. Okay, the first scenario, you have 1D, right? Okay, the diameter is about D. Okay, let's just say this one is 10. Okay, just take the one is 10 centimeter. The pump power that's needed to pump it is 16 horsepower. Okay, can you imagine? It requires 16 horsepower in order to pump this. However, right, the moment you increase the D from 10 to 20, it will be able to reduce the pump requirement by almost 16 times. Can you believe that, fellas? Right, the pump requirement by just doubling the diameter, you will be able to increase the pump requirement by almost 16 times. Right? 16 times. How can we foresee this? It's actually from this equation. Okay, it's actually from this equation. Right? Now, if I were to rewrite this, okay, if I were to rewrite this, right? How did I get that? Okay, it's actually from this fella called, or what do you call his name? All right, okay. Just share. Right, I'm gonna be sharing my white screen. Can you see this, fellas? Boleh nampak eh? Can you see that? Boleh tengok eh?
Boleh, sir.
Okay, right, I'm gonna have to write this one down again. V dot equals to delta P. I don't remember the equation. Okay, just like you fellas. Okay, V dot equals to delta P. Okay, from the Versoy. Okay, pi d4. Right, pi d power 4 divided by 128, 128, the viscosity, and then L. Right, so I believe this is the equation. All right, okay, this is Pois, how pronounce Poiseuille, something like that, right? So this is the law. Now, if you were to rewrite this, okay, rewrite this. Okay, so you're gonna have delta P, delta V is a function of V dot 128, okay, mu L over pi d power 4. Okay, so this is your the change of pressure or the pressure loss. Okay, the pressure loss, okay, I can rewrite this. The pressure loss, just put this one as center. Okay, pressure loss as a function of the volume flow rate, the mu, the viscosity, the length of the pipe, pi d square. According to this equation, yeah, you know what? Actually, if you just increase the d, right? If you increase the d, you will reduce this because delta p is inversely inversely proportional to the d, right? Is inversely, not only inverse proportional, but it's a power of 4. The moment you increase this one will go down. Okay, so this is according to the fella. Okay, according to the fella. So that's why if you increase the D, the diameter of the pipe, okay, this is one of the solutions. Yeah, if you increase the diameter of the pipe, you would be able to decrease. Okay, you will be able to decrease the pressure loss. Okay, that's what being said. Okay, in this equation, right? In this equation, simply imagine by just increasing the D 2 times. Okay, D being 2D, like 10 becomes 20. you are decreasing the requirement of the pump from 1 to 16. The pumping power requirement for laminar flow piping system can be reduced by a factor of 16. Okay, by just doubling the pipe diameter. Can you believe that? It's actually because of D here, right? Is D here is a 2 power 4. I no, no, no. Okay, 2 power 7 different. Okay, no, 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 not this. I think it's 2 power 4, 5. Yeah, I think 16. 2 power 4, right? Okay, but okay, I'm just telling you that by just doubling this, that could decrease the power of the pump by 16 times. Okay, so that is the one of the benefits, right? One of the benefits of one of the solutions that we can use in order to decrease the pump power. Okay, decrease the pump power. Okay, so that we could reduce the pressure loss. So if I were to ask you, how would you suggest? Okay, what would you suggest in order to decrease the pressure loss? Right, one of the solutions is to increase the diameter from D to 2D. This is one example from given from the book, right? Given from the book, you can increase the diameter, which is one of the easiest way that you could do. Okay, you increase the diameter, it will increase. It will somehow decrease the pump power, and that's it. All right, that's it. There are many others that you can do, but one of the best is to increase the diameter. Okay, so this is the last slide, fellas. Okay, this is the last slide. Right, the pressure drop, okay, equals to the pressure loss, okay, in the case of horizontal pipe, but this is not the case for inclined pipes. We're not gonna look into much of inclined pipes, okay, but what I do want you to understand is just horizontal pipe as well as vertical pipe, okay, that is, okay, that's good enough. Okay, pipe variable cross-sectional areas, okay, we're not gonna look into inclined pipes or pipe with variable cross-sectional areas, okay. At this point, just understand the basic, okay, just understand the basic flow of pipes, okay, being similar diameter, being horizontal or vertical, right? This can be demonstrated by writing the energy equation, incompressible warm flow. Okay, this, okay, what is actually the essence of Bernoulli equation. Okay, the essence of Bernoulli equation plus the head of the pump, and then the head of the turbine. Then you reorganize this. Okay, then you can say that pressure drop. Okay, delta P pressure loss. Okay, is given procession is equivalent horizontals. Okay, if you have the horizontal. Okay, mm, if the elevation is the same, okay, being the Z is the same, Z1 and Z2, right? The flow section does not involve any work device, okay? The cross-sectional area is constant and the various velocity is V1 equals to the velocity profile 1, 2 is the same, okay? The flow, the pressure drop and the pressure loss, okay, are equivalent, right? The pressure drop and the pressure loss is equivalent the moment you fulfill this scenario. Z1 equals to Z2. Okay, Z1 equals to Z2, and then H pump equals to 0, and then V1 equals to V2, and then alpha 1 equals to alpha 2, right? So this is just some additional info that you will need. But I do want you to concentrate more on this, okay? Just this. Alice, okay? Just concentrate more on this. And then we shall do exercises based on this. And how would you use this in order to work out the pump requirement for the circular pipe horizontally. Okay, so I think we shall stop here and then we shall look into some of the examples from the book. Right, some of the examples from the book. Right, okay, I'm gonna be um okay, the book example. Right, the book example is this. Okay, we're gonna go straight to 8.2. Okay, the water at 40 Fahrenheit. Okay, this is in Fahrenheit, yeah. Okay. This is in Fahrenheit. Right, I think I'm gonna use my own. Okay. This is example from the book as well. Okay, this is an example from the book as well. Water at 5 degrees Celsius, rho equals to 1,000 kilogram per meter cube. And then you have the dynamic viscosity, 1.5 times 10 power negative 3. Okay, kg meter second. Okay, is flowing steadily through a 0.3 centimeter diameter, 9-meter long horizontal pipe at an average velocity of 0.9. This is the example from the book, fellas. Okay, Determine the head loss, the pressure drop, the pumping requirement to overcome this pressure drop. Okay, this is an example from the book. Now, how would you do this, fellas? The head loss, okay, water at 5 degrees Celsius, is flowing steadily through a zero point 0.3 diameter, 9-meter long horizontal pipe, at an average velocity of 0.9 meter per second. Okay, if I were to do this, right, put this aside. Okay, this is the example from the book. Right. First off, right, collect all the information. Okay, you need to collect all the information from the. Can I just make this one smaller? Right, there you go. So I could write over here on this one. Mhm. Okay, I really hope you can see this. Okay, so the water, um, the temperature of the water, okay, the water equals to 5 degrees Celsius. You have the raw of the water is 1000 kilogram per meter. Right, you can do this together with me, fellas. Okay, write it down if you don't have your book. And then you have your mu, okay, equals to 1.519 times 10 power negative 3. Okay, collect all information that you have. The diameter, dh, okay, it's not p, d, equals to 0.3 cm. And then the length, I believe the length of the pipe is 9 meter. The horizontal, the length of the pipe is 9 meter. Length of the pipe is 9 meter. And then average velocity, okay, that's good. Average velocity is 0.9. So you have average velocity equals to 0.9 meter per second. Is it? Yep. Okay, so you are required to find the head loss equals to question mark. The okay, delta PL loss. Okay, question mark. And last but not least is the pump power to overcome the pressure drop. Okay, the pump. Okay, the pump power according to this. Um, okay, the pump, they put L. Okay, with the pump, L, okay, equals to question mark. So these are the stuff that you need to find. Okay, how would you do this, Wallace? How would you do this? How would you do this? Okay, first, what would be the step? Okay, after you have collected all the information now, um, remember when you're solving problems, okay, when you're solving any problems given in my class, I would want you to write this because I would give you marks. Okay, I would give you marks, Wallace. Um, sorry, this one is the unit. Okay, kg per meter second. Right. Remember to give all the required information. Okay, when you're answering your questions. Yeah. Okay. Give all the required information you can get directly from the question. Okay. And then these are the things you need to find. Sometimes I will give marks on this, fellas. Okay, remember that, yeah? Okay, you need to find the HL, delta PL, and then the work of the pump. Now, where do we find all this information? Let's go back to the lecture notes. Go back to the lecture notes. This is where you find all the required information, fellas. Delta P equals to F. So this is the pressure loss. This is the head loss. Okay, is F L over D. Okay, it's different. Yeah, I mean, and then you have to find the F. F is different for laminar. It's different for turbulent. It's different for transition. So you have to be careful. So you need to determine the F first. If the F is okay, if the F is less then 230 for the number, then is Laminar. If it's like in between 230 and 4000 is transition, is greater than 4000 is turbulent. So you need to decide a lot of things to decide here, fellas. Okay, if it's Laminar, so this is the equation for Laminar. Because for turbulent, the on is going to be different, right? We'll discuss turbulent in our next class. However, this is the example for Laminar, which I presumed you're going to get Laminar, okay, value of Reynolds number. Okay, then you're going to find F, okay, F using this equation, the head loss using this equation, right? Can you try this, Wallace? Rachel, try this? Because I think for this one, the first step that you need to do, I think the first step is, step one is to determine the regime, okay? Step one is to determine the regime, right? If you agree with me, I think step one is to determine the regime, whether it's laminar, whether it's turbulent, or whether it's transition, okay? Okay, transition. So whether it's laminar, turbulent, or transition. So you will need to determine this by using the Reynolds number. So the first stuff that you need to determine is the Reynolds number. Okay, Reynolds number is given by rho v d over mu. So find this version. I think from this information given, you have your rho, you have your velocity, you have your d divided by mu, which is straightforward. Okay, which is quite straightforward. You just fill them in. Okay, you just fill them in. You fill them in. You fill the rho. You fill the velocity. You fill the d. You fill the mu, and then I think you get this. I'm just gonna get the direct value from the book. It's 1777. Okay, I repeat, the value from the book is 1777. But first off, what is the unit, fellas? What is the unit for an odd number? Can anyone tell me what's the unit for an odd number?
Dimensionless.
Exactly. Okay, thank you for the answer. Is I think we developed this in the previous class. Is one of the non-dimensional parameters. Non-dimensional parameters meaning they don't have dimension. They don't have dimension. They don't have unit. That is why the Reynolds number is just given by its number. That's it, right? You don't bother about unit. This is the unit for Reynolds number. No unit. Okay, 1777. Okay, now 1777. Let's go back to the lecture. So tell me, which regime is it? Is it laminar, transition, or turbulent?
Laminar.
Laminar.
Everyone agrees on laminar?
Yep.
Right. You all agree it's laminar? Okay, according to this, anything less than 2300 is laminar. Now, what is our Reynolds number? Our Reynolds number is 1777. Thus, it is laminar. Okay, it is laminar. Now, why do you need to determine whether it's laminar or not? Because you need to determine the F. Okay, now let's write down the equation for the delta P, which is quite long. All right, okay. So number two, okay, the moment you know this is laminar, so it's laminar. Okay, it's laminar. Now, step two is find F. F for laminar. Okay, find F for laminar. F for laminar, actually the F for laminar is 64 over F over a Reynolds number. I think this what it is. Yeah, I think the F is 64 over a number. This is specifically for just laminar. This is specifically for just laminar because for turbulent it's going to be something else. Turbulent is much difficult than this, right? F is given by this for just laminar, fellas. Remember this. And then from this F, I think then after that, okay, the question asks you to find the HL, right? Then HL is a piece of cake. Then HL equals to right? HL equals to delta PL over rho G. Delta PL over rho G. Or you can write this one down as F L over D, F L over D, F L over D, V square over 2G, V square over 2G, right? V square over 2G. Now, tell me, do you have F? Do you have F? Yes, I think so. Do you have L? Yep. Okay, sure. Well, sure does. You have D, obviously. You have the V, well, given here. And then do you have the G? G is the gravitational force, which is, well, you can find that, right? Don't worry. So, okay. So, 2G. So you just work out. And then this is the answer given by the book is 4.46. 4.46 meter, right? That's it. Can anyone tell me what does this value mean? What does it mean by this value, fellas? 4.46, right? What does it mean by this value? The HL equals to 4.46. Are you just calculating without knowing what it is? What is 4.46, fellas? 4.46 is the head loss. What does it mean by the head loss?
The additional height.
Yeah, additional height of void. Okay, let's go back to the lecture notes. Okay, if you don't, if you can remember, the additional height, yes. Okay, additional height. The fluid needs to be raised by pump, right? We are losing this. We are losing this height. This is the height that supposedly we get without friction. Okay, this is the height that we should get without friction for all these scenarios, for all these requirements. Yeah, for all these. If the water is at 5 degrees, if the row is 1,000. It's not 100, it's 1,000. Okay, kena coba balik ya. Okay, it's 1,000 Okay. Okay, if the viscosity, if this are the condition of the water, right? And then the head loss is this one. This is the height that we will lose. Okay, this is the height that we will lose. Okay, which must be supported by the pump. Okay, which must be supported by the pump. Okay, due to the friction. Okay, due to the friction. So this is the additional height that we must provide. So if we were to provide the what they call that, the height, okay, if we were to provide to the 10 flow is about 20 meter. Okay, let's assume it's 20 meter, right? So you, instead of supplying the water to 20 meter, you have to supply to 20 plus 4.46. Otherwise, it won't go up to 20 meter. So it becomes 24.46. In order to pump to 20 meter, you have to add 4.46 more. You know what I mean? Okay. So this is the height that we must pump in order for it to achieve 20 meter. So if you were to pump to just 20 meter, right, without any knowledge of this, okay, without knowledge, you pump to, okay, you intend to pump 20 meter, you pump, that only, I think, this one minus 4 is going to be 15 meter only, right? Initially, you want to pump to 20, but you will end up pumping the water to just 15, right? Due to friction, right? This is basically what it means. Okay, this is the losses. Losses. It should have been 20, but becomes 15 due to the losses. Okay, so this is the head loss, 4.46. All right, and then the next one. Okay, pressure drop. Okay, for pressure drop. Okay, pressure drop is again, all right, okay. Formula is too long. FLD, rho V over 2. Oh, it's actually simpler. FLD is FL over D, V2, okay, over 2. Total. Rho V2, okay, rho V2. Okay, मतलब rho. Okay, so FL over D, V rho V2 over 2. So I think you still have all the information, L over D, V square rho, blah, blah, blah. I think for this, the answer from the book is 43.7 kilopascal. Okay, this is the pressure drop. Okay, yang inilah yang menyebabkan apa ni, water tak sampai. Okay, pressure kat rumah. Jadi kalau you nak pump, okay, let's just say you want to pump like 100 kilopascal. Okay, you want to pump the water at 100 kilopascal. okay, 100 hectopascal, you have to add another 43, okay, in order to get to your house. Okay, these are the losses, fellas, losses. So instead of pumping at 100, you should add 43.7 more in order to get to the required place. Okay, you have to add 43.7 kPa more. Okay, this is the losses. Okay, the extra, right? Now, what do you need this value for? Because actually 5, we can determine the work from the pump. Okay, the work from the pump equals to the volume flow rate multiply with the delta, delta P L. Okay, so this is it, right? I think for this, the velocity is given. Okay, this, I think the velocity is given. Velocity is given here, 0.9. And then you have this, okay, 43.7 kilopascal. Okay, you just multiply. Okay, you just multiply, and the answer that you get from the book would be 0.28 watt. Okay, this is the answer you get from book. Okay, what does it mean by this? 0.28 watt is the power that you need to pump with all the losses. Okay, what is 0.28 watt? Is the pump power that you need to pump additionally, okay, in order to address the losses. Okay, in order to increase it 4.46 more, in order to increase it 4.43.7 more. Okay, so this is the pump power required in order to pump the water, okay, to its respective height, okay, or to its respective meter, okay. So the diameter, the L, 9 meter. So this, okay, to pump the water through this in this requirement. So these are the information, the losses that you will get, the pressure drop, as well as the pump that is required in order to do so. So that would be it. Okay, that would be it. Okay, so that would be it. All right. I think I'm gonna stop here. All right, I think I'm gonna stop here. I do have one example that I want to give you a try. Please can you attend? Um, okay, whether or not should I give you now? Because on Friday, on Friday, okay, because on Friday we're gonna try the turbulent. Okay, I'll give you your exercise. Okay, I'm going to enable this. I want you to give it a try, and then on Friday we're going to try this the turbulent part. All right, I'm going to try the turbulent part. Okay, please scan, and I am going to enable the exercise. Okay, I want you to give this one a try. Okay, this is exactly is quite similar to the one that we just did, right? It's quite similar to the one that we just did. Okay, I want you to give it a try, and then I think it's quite straightforward, isn't it? I think it's quite straightforward. Okay, it's quite straightforward. You just apply formulas. You find all the you need to know the regime first. Okay, whether it's laminar, because we just covered laminar. Okay, that's the thing that makes it easy. Okay, in the next part of the lecture, okay, we'll try different regimes. You're gonna have we're not really gonna use that equation anymore. We'll be looking at the chart later on, okay, which is gonna be much